Problem E from Codeforces round 877. We are given an array A of length n and we have to count the number of arrays B such that A is a subsequence in B and length of B is m and all the elements of B are within the range 1 to k. So in this video I'll be explaining geothermal solution from his live stream. But what's new is that he did not elaborate on one crucial point which I didn't immediately understand from his live stream. It might be obvious for him, but I think it required a slightly more elaborate explanation. So that's why I'm making this video. So the general idea is that we are counting the complementary answer. Basically, we are taking the total number of arrays such that length is m and array elements are within k. That will be k power m, and we are subtracting the arrays b which does not satisfy the condition being subsequence condition. I am denoting this as x. So the question is how to calculate x being the number of arrays which do not contain a as subsequence, we are dividing them into n buckets, and ith bucket will have a0 a1 dot 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 ai minus 1, this as subsequence, exactly this as subsequence, and it should not have ai. For example, this bucket will not have arrays which contain a of 1 after a of 0, because if they belong to this bucket. So these are disjoint, as you can see, like so we can just add the answer of each of these to calculate x. So how to calculate the number of arrays in each bucket? For example, let's say we are calculating the arrays b such that a0 a1 dot 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 ai minus 1 is a subsequence. How to find this? Let's look at an example. Here n is 4 and the array is 1 2 3 4, and I am choosing I as 3 and m as 7 and k is, let's say, 5. Basically we want 1 2 3 as a subsequence in the array B which has 7 elements. So we are basically putting 1 2 and 3 in this 7 blank spaces. So number of ways to choosing this is 7c3 ways. And let me show you a couple of ways. In this I am putting 1 in the second position, 2 in fourth position, 3 in sixth position, and in this I am putting 1 in second position, 2 in third position, and 3 in sixth position. So the point I mentioned earlier, right, that geothermal didn't elaborate on one crucial point, that is this: how to fill the rest of the elements. He vaguely mentioned like there are k minus 1 choices for each of the blanks, but this point was the thing that was not obvious for me. Why k minus 1? So then I started to thinking, can I put anything in these blank spaces? For example, can I put a 2 here? It turns out you cannot put a 2 here, because while filling this set of arrays there might be one way in which we are putting 2 here, 5 here, 2 here, 5 here, 5 here, and one other way of choosing the 3 positions in the 7c3 ways is this one, and here we could have put 5 here, 2 here, 5 here, 5 here. Basically we will be over counting this array. Basically we will be counting this more than once, which we do not want. We want to count these arrays only once. So how to prevent this overlap? The rule that I came up with after some thinking is this. We cannot, there is one obvious thing that we cannot have 4 here. Why? If we have 4, then it will belong to the bucket which has 1 2 3 4 as subsequence, which we do not want to do. We are only calculating this arrays which has 1 2 and 3 as subsequence. So it is obvious that 4 should not come after the 3. So all the positions after 3 should not have 4. So these have should not have 4, therefore k minus 1 choices here. But between 2 and 3 can I have between 2 and 3 I cannot have 3. Why? If I put 3 here, if I disregard my rule and put 3 here, again there will be overlap in this case, because I can put 3 here and fill the rest with 5, and there will be overlap. But if I follow the rule that between 2 and 3 there cannot be 3, so there can be 3 here, 3 here, 3 here. Why? Let's say I am putting 3 in the last position. You can argue there might be another case where we are choosing the 3 way 1 and 2 3 position in such a way that 3 comes in the last position. But according to my rule, there cannot be 3 between 2 and 3, so 3 cannot come here. So the 1 2 3 3 sequence which was here will not come here, because between 2 and 3 3 cannot be there. So again we have only k minus 1 choices. So again here k minus 1 choices. Again here we cannot put 2, so k minus 1 choices, and again here we cannot put 1, so k minus 1 choices. So the rule to fill the other gaps is that between any two numbers we cannot have the next number. So here we cannot have 2, here we cannot have 1, here we cannot have 3, and in the end we cannot have 4. If we do have them, then some other way of choosing that there are 7C3 ways, right? In some other way there will be overlap, as I showed in a couple of examples. So we have k minus 1 choices for m minus I blank spaces. So number of ways to do will be k minus 1 to the power m minus I, and this is number of blanks will be same for all this MCI ways of choosing I spots, and so the answer will be MCI choose k minus 1 to the power m minus I for all the buckets. So I equal to 0 to n minus 1, and we subtract the x from the total arrays to get the answer. One more crucial point which was not explained is, here we were calculating number of arrays B which has A0 A1 dot 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 AI minus 1. Basically there are I elements as a subsequence, right? If we go back to the question, we just wanted to calculate the expected output of the question was calculate B such that A0 dot 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 AN minus 1 is a subsequence. So why are we subtracting these? Let's say this is uh, let's say count of I. So in the solution I propose, I am subtracting uh, I am saying the answer is k minus m minus sigma I equal to 0 to n minus 1 count of I. This is what we are doing, but the expected output in the question is just count of n. Why cannot we just directly calculate this as m choose n k minus 1 to the power m minus n? Because count we defined count of I as m choose I k minus 1 to the power m minus I. Sorry, it's not sigma. And we were counting summing it over 0 to, this is for I equal to 0 to n minus 1. So why not apply this formula to I equal to n? The problem is, let's say there are let's say a equal to 1 2 3 4, and again m equal to 7, k is equal to 5. Let's say one of the m choose n ways is 1 2 3 and 4. We can fill here, we cannot fill 1 here, we cannot fill 2 here, we cannot fill 4 here, but this has no such restrictions. So these things have k minus 1 choices and this has k choices. So in some other combination of putting 1 2 3 4, let's say 1 2 3 4, here there will be k choices, k choices, k choices. So number of arrays with this template will be k to the power 3, but in the previous this template was k minus 1 to the power 3. Sorry, am I missing something? Okay, I think, sorry, k minus 1 to the power 2 into k to the power 1. Basically the number of positions after 4 varies. Here it is 2, here it is 1. So basically I added an extra space, so my bad. So there were only 3 blanks, one here, one here, and one here. Here we could not have 2, here we could not have 1, here we could have anything. So here the answer was k minus 1 square to into k power k minus 1 square into k. Here the answer was k to the power 3. So for different way of choosing, so among the different MCN ways, each has some k minus 1 power x into k power y, such that x plus y is m minus n. Y is basically the number of blanks after the last number. So this doesn't come out as one neat formula. So that's why it's not, we cannot directly calculate count of n. But for everything else, there will be one other element to the next which we could not have. So for example, for the case of 1 2 3, okay, let's say 1 2 3, here we could not have 4, so again it turned out to be k minus 1 choices. Here we could not have 2, we turned out to be k minus 1 choice. Here cannot have 1, so k minus 1 choice. So this k minus 1 was there in every other position. So the formula turned out to be simple, m minus I. But here there will be k choices after the last element, and before that k minus uh, one choice here. So actually I made a mess. I think it should be sorry, k minus 1 into k square. Anyway, the point is the k minus 1, the power of k minus 1 and k differs depending on how you choose 1 2 or 3 4. That's why we couldn't directly count of n the way we did for the way we did count of I for 0 to I n minus 1. So yeah, as I said before, there is no single formula to calculate count of n, but we can calculate it iteratively. How we can do this is, let's take the same old example where a is equal to 1 comma 2 comma 3 comma 4, m equal to 7. There are 7 positions. Let I be the position of last element of a, which is 4. This is 0 based index. 1 2 3 4 5 6. This is m minus 1. This is I. For example, if I fix the last element here, so there are I spaces here, and I have to choose n minus 1 equal to 3 to place 1 comma 2 comma 3. For example, 1 2 3. So here we cannot have 3, we have k minus 1 choices. Here we have k choices, here we have k choices. So number of arrays would be I choose n minus 1 into k minus 1 to the power I minus n minus 1 into k to the power m minus 1 minus I. This is 2 and this is 1, and we sum this over I equal to n minus 1 to m minus 1. The problem with this iterative method is the time complexity is O of m minus n, but m is of the order of 10 power 9. So this will give us TLE.